Good day and welcome to the Moscow Telecommunications Seminar. Our today's speaker is Alexander Krotov. Alexander is a senior researcher at the Institute for Information Transmission Problems of the Russian Academy of Sciences and Higher School of Economics. He has received a Ph.D. degree in telecommunications from Moscow Institute of Physics and Technology in 2020. Today he will tell us about different algorithms for selection of modulation and coding schemes in Wi-Fi networks. Alexander, the floor is yours.
Hello everyone, I am going to tell about rate control algorithms in Wi-Fi networks. Wi-Fi standard defines multiple modulation coding schemes, also known as rates. Higher data rates provide higher throughput, but at the same time they require better channel conditions, better signal-to-noise ratio. The standard doesn't specify how the station should select rates to transmit. So different devices implement different algorithms, and they can be chosen by vendors and users. Many rate control algorithms have been proposed in the literature, and many algorithms have been developed in devices. They can be divided into two groups: measurement-based algorithms and sampling-based algorithms. Measurement-based algorithms require that channel quality information is provided to the rate control algorithm. Because of that, some of these algorithms require modification to the standard, for example, to send measurements in acknowledgements. And other algorithms that can be implemented use information that is already provided, such as RSSI, to select initial rate. But this information is not enough to maintain optimal rate, so they have to use sampling at the same time to select better rate when they have collected the statistics. More practical algorithms are sampling-based. They collect the statistics of successful and unsuccessful transmissions down using different rates. And there is a long history of these algorithms being implemented in real devices, such as after-rate fallback, adaptive after-rate fallback, and now one of the most popular algorithms is called Minstrel. It's implemented in Linux, and it's widely used in NSE simulation environment to evaluate the performance of Wi-Fi networks. Let's take a look at the Minstrel algorithm. The Minstrel algorithm estimates successful transmission probability for each modulation coding scheme and uses known rates of each modulation and coding scheme. Before transmitting each frame, Minstrel selects 4 rates. First, it selects 2 rates that have the highest estimated throughput. Then it selects the rate with the highest success probability, and in the end, if none of these rates can be used to successfully deliver the frames, it resorts to the lowest MCS. To avoid getting stuck using non-optimal rate, Minstrel also implements a look-around rule. 10% of the time, it uses random modulation coding scheme instead of the second best on the first step. The reason Minstrel was designed like that is not a result of some research, but mostly a result of adapting to a particular device for which it was developed. This device had a queue that is accepted from the driver. And the driver has to define 4 rates and 4 number of transmission attempts for each rate. Later, the Minstrel was adapted for newer standard, but retains the same structure. And many similar algorithms have been designed like that because of the limitations of the wireless chip. If you want to design a better algorithm, we need to review design decisions from scratch and start from the problem statement. Rate control problem is very similar to the classic multi-armed bandit problem with Bernoulli rewards. There are n arms corresponding to data rates, and when you play an arm, you get a reward with the success probability of this transmission rate. The reward is either 0 or the transmission rate of this modulation coding scheme. In the literature, there are many algorithms to solve this problem. One of the simplest is a greedy algorithm that always estimates the success probability based on the number of successful transmission and number of unsuccessful transmission, and then uses MCS that provides the highest estimated throughput. However, this algorithm can get stuck using non-optimal rate. For example, if the first transmission on the optimal rate was unsuccessful, this algorithm will no longer try this rate at all. And to ensure that this algorithm explores other rates, there is a epsilon greedy addition to this policy that's defined like the lookaround rule for Menstrel. Epsilon % of the time, this algorithm tries a random rate. But it still doesn't solve the exploitation trade-off. How do we choose how much time do we want to spend trying random rates? If we collect a lot of statistics, we probably want to stop trying random rates, but the algorithm doesn't define how we do this. So there is another algorithm that tries to optimize the number of times it tries non-optimal rates. It works as follows. First, we select some prior distribution of success probabilities. Usually it's a uniform distribution, but if you have some more information before the start of the algorithm, you can put it into this probability distribution. Then we collect the statistics of successful and unsuccessful transmission on the data rate and apply bias rule to calculate the posterior probability of the distribution. After that, we use estimated probability distribution to sample estimated success rate and use estimated success rates for all the modulation coding scheme to select the best perceived rate. This algorithm was actually the first algorithm proposed for the solution of this problem, but there was a long time until it was proven that it provides optimal solution for different environments, different real success probabilities. If we look at our problem and how we apply Thompson sampling algorithm to it, the formula simplifies. We use Bernoulli rewards, so numerator becomes just a binomial distribution, and in the denominator there is a beta function that is used to normalize our probability distribution. In practice, when we collect the statistics, for example, if we collect that there was 6 successful transmissions and 1 unsuccessful transmissions, this distribution, called beta distribution, shifts towards real success probability and becomes narrower as we collect more statistics. So eventually, it converges to the real success probability, and we stop exploring different rates, because for different rates, we have information that they have low success probability like this. Let's make a simple experiment to evaluate these algorithms in practice. To compare these algorithms, we define simple testing environments. We use data rates from the standard. In this case, I have used .11ac data rates. There are 10 different data rates. And for success probabilities, I have sampled them uniformly with the constraints that higher data rates should have lower success probability. And after that, I have ran these strategies and collected so-called regret. Regret is the difference between the amount of data that we could have transmitted if we used ideal algorithm and the amount of data that we have transmitted using our policy, for example, greedy algorithm or Thompson sampling. And after that, I have averaged these results over multiple runs and plotted the mean result. As can be seen, greedy policy has linear regret because in some of these runs, it gets stuck using non-optimal rate. And after that, regret will increase with the time. On the other hand, epsilon greedy policy will eventually collect enough statistics for each rate, but because of the look-around rule, similar to what is used in Minstrel, it will still spend 10% of the time using random rates. And because of that, regret continues to grow. While Thompson sampling achieves sublinear regret, and eventually regret almost stops increasing. Because Thompson sampling is proven to be asymptotically optimal, it doesn't mean that it's the best strategy that we can implement. As a new standard increase the number of data rates, and there are multiple different options that we need to explore, like different channel widths, or maybe the number of spatial streams if we use MIMA, and so on. The number of rates that we need to try increases. And if we have a limited time to explore these options, it becomes important that we spend less time until we converge to the optimal rate. And the theory doesn't tell us anything about how fast Thompson sampling converges. If we want it to converge faster, we need to take into account the structure of different data rates. For example, if we know that we have tried MCS 7 and it has very low success probability, we should not try higher rates. But Thompson sampling will explore them anyway, even if there are 100 more different rates. One of the approaches proposed in the literature is to assume that data rates have a unimodal distribution. So there is an optimal data rate, and as we go away from the optimal data rate to lower modulation coding schemes or higher, the throughput will steadily decrease. But in practice, it's impossible to prove that it's true for Wi-Fi networks. And on the slide, I show a simple example that data rates increase with the number of MCS, and success probability decrease as the number of MCS increases. But if we multiply them, we don't have a single mode of the distribution. There's MCS 6 and there's MCS 8, but as you go from one to another, data rate decreases. So the assumption doesn't hold. And if we use algorithms that use this assumption, we can end up using this data rate and explore only data rates for MCS 5 and MCS 7, but we'll stop exploring MCS 8, which is actually optimal. So another approach is to take into account the structure of success probabilities directly. We can calculate true posterior probability given that we assume that prior probability is uniform and can be constructed as Dirichlet distribution and with simple transformation. And we can calculate relative probability given that we know the statistics of successful and unsuccessful transmissions. But the problem is that to implement this algorithm, we will need to sample success probabilities from multidimensional distribution. And this problem is computationally hard. Even if we don't use simple algorithms like rejection sampling and use state-of-the-art algorithms like Markov chain Monte Carlo, it's impossible to implement this algorithm in real devices. Because even in this simple experiment, it was impossible to compute success probabilities from this distribution once we collect more and more statistics and the distribution becomes too narrow. So if you want to design an algorithm that takes into account the structure of success probabilities, we need to take a step back and look at how we can design the algorithm in another way. Instead of looking at the success probabilities directly and trying to find the structure there, we can model our wireless networks as the channel with some parameters that define the channel quality. Such a parameter for the wireless channel is well known. It's a signal-to-noise ratio. And what is good about such a parameter is that it is single-dimensional. So it will be easy to sample from the distribution if we somehow estimate the distribution of signal-to-noise ratio based on our measurements. So we want to design a rate control algorithm in two parts. First of all, we need a channel model that we will update based on observations obtained from the real system. And then we want to use decision-making part. In this case, we can use the same Thompson sampling approach to select actions. That's modulation calling schemes that we will use to transmit data frame to the real system. To model the distribution of the channel parameter, we can use an approach known as particle filter. We'll approximate the distribution of this parameter, that is the difference between signal-to-noise ratio and transmission power, as a number of particles. Each particle is characterized by its position that corresponds to the value of the parameter and probabilities that we will select this particle. If we have enough particles like this, we can approximate probability density function of the estimate parameter well enough. Particle filter algorithm will work as follows. When we need to select MCS, we will estimate success probabilities given the signal-to-noise ratio and multiply it by the data rate. Then, based on observations that we obtain from the network, like if we successfully or unsuccessfully transmitted, we can update probabilities of the particles. And then we can predict how particles move with the time. Because stations move, we need to predict that particles will also move at some speed in a known direction. And for that, we model that particles move according to the Wiener process. Let's evaluate how this algorithm performs in practice. For that, I have constructed an NSE simulation that consists of one access point and one station placed in 10 meters from each other. And access point periodically changes its transmission power. Rate control algorithm has to adapt to these changes. In this slide, I have presented the result for Minstrel algorithm, Thompson sampling algorithm with different decay rate to forget all statistics that is irrelevant because the channel changes, and particle filter. Because particle filter estimates not the probabilities, but it estimates the path loss, it can adapt to transmission power changes. So we don't have to forget all statistics. It can still be used. As can be seen, Thompson sampling has some optimal decay rate, while particle filter always outperforms Thompson sampling algorithms and Minstrel regardless of the parameters that we choose. Another scenario that I have tested is two Wi-Fi 6 links that use special reuse mechanisms of Wi-Fi 6. And in this case, I have measured latency of the transmission in these two links. Again, as can be seen, particle filter decreases latency significantly compared to known algorithms because it can adapt to the transmission power changes in this case. Still, this algorithm was designed based on the sampling, and it was designed for a particular problem of changed transmission rates. But there are different problems that we need to solve as there are new applications of Wi-Fi networks and there are new standards. If you look at the new applications, currently there are a lot of applications related to virtual reality, for example, that need low latency to transmit video frames. So far, the algorithms we have looked at optimize only for throughput. But if we want to optimize for latency, we need to design these algorithms differently. There's one article in the literature that I have found that tries to place constraints on the Thompson sampling to make sure that for each frame, the delay does not exceed some threshold. For example, Thompson sampling can select one frame from the queue and try different data rates there. But if it's an important packet like a block arc agreement frame or TCP connection establishment, if Thompson sampling uses this frame to try different rates, it's possible that the frame will be simply lost by the number of retries or exceeds the timeout that is after which this frame will not be useful. So one of the directions that new rate control algorithms can be developed is to explore different constraints and different KPIs like latency and other requirements of new applications. Another development direction is that new standards use different technology to transmit data, like Wi-Fi 6 introduce OFDMA and other mechanisms that are well known from cellular networks, like buffer status report and sounding. So in this case, we need to use not only the sampling approach, but measurement-based approach. And there is a question, how do we use these measurements and how do we combine them with the information that we obtain from measurements that we receive by sampling? So to conclude, existing algorithms that we usually take for granted and that are widely used in the performance evaluation, like most of the papers currently use Minstrel, were not actually designed for the requirements of the applications that we use in the networks. And there is a simple approach like Thompson sampling that can be used for performance evaluation that are much easier to analyze when you need to understand the performance of the system that you design. And also in highly dynamic environments, there are better approach, like particle filter can be used if stations move or if they change their transmission power. And in the end, there are various new applications and new technologies that will need differently designed rate control algorithms. So if you have questions, you can ask them in the chat and I will answer them now. So one of the questions is, should rates take into account Wi-Fi MAC overhead? These data rates that we use to estimate data rates should take into account overhead and the size of the frames that we transmit in practice. In this simple scenario, I have used data rates from the standard, as if we transmit data frames without the header. But in the NSA simulation, Thompson sampling approach that I have implemented is using data rates that takes into account all the overhead and frame data size. Before we transmit each frame, we select these success probabilities, but data rates that we use to calculate estimated throughput and actually select the MCS that we will use, we can multiply by the data rate that takes into account all the overhead and the particular frames that we will transmit. About this slide, there is a question if grid algorithm will perform better if we choose different epsilon. It's possible to optimize grid algorithm by choosing different epsilon, but in the end, it will still have linear regret. Because as long as epsilon is non-zero, we will spend some % of the time using random rates. And some part of the times that we use random rates, if we sample these random rates uniformly, we will use non-optimal rate and increase regret. So it's impossible that greedy algorithm with optimal epsilon will have lower regrets than Thompson sampling. Another question is it possible to implement particle filter in real device? Particle filter complexity depends on the number of particles that you estimate, but all these particles you can update in parallel. So it's possible to implement this in real devices if you have special hardware that can process these particles in parallel. Another approach that can be used to reduce the complexity is to use not particle filter, but some approximations, maybe Kalman filter that is used to estimate normal distributions, or some other distributions that are easier to update that approximate the distribution of the signal-to-noise ratio in real networks. Another question is if you can improve the particle filter by using a different particle movement procedure instead of the Wiener process. In this example, I've used the Wiener process because I have no information about how the signal to noise ratio changes in the network. But it's always possible to improve the algorithm by having a better channel model. The problem with constantly improving the channel model to fit your particular network is that if the channel model is wrong and can approximate the real network, then you have the same problems as you have if usually when you take wrong assumptions, like if you think that your channel has a modality property and use channel models that can only approximate channels that has this property, then you'll have worse performance than if you didn't try to specialize your channel model. So it's better to use general enough channel model if you don't know in advance where your algorithm will be used. Another question is about URLC scenarios, that we cannot test the channel for high rates because we are not allowed to lose packets. So how do we design algorithms for URLC? When I talked about low latency requirements, I was mostly talking about the applications that have low latency requirements of a typical video stream, for example, or something like that. But if you have URLC requirements, like you are not allowed to lose even one packet, then the only approach I see to improve rate control grid for this case is to use measurements in advance, like transmit special frames that don't have this requirement on the packet loss ratio, such as special sounding frames. Basically, it means that you need to use measurements in your system. Another question is
Alexander, sorry, just to clarify, so do you believe that so some sampling algorithms like particle filtering or something is inapplicable to URLC because they rely on the testing of the channel?
This depends on the requirements on how many frames can you lose, but if you are not allowed to lose even a single frame for each MCS, or at least a few frames to estimate which MCS you can use, then you cannot use your frames for sampling.
Mm-hmm. So from your side, the only way
even the particle filter
to measure SNR directly.
Yes, it's better to measure SNR directly with special sounding frames if you need to transmit special frames to estimate success probabilities anyway. It's better that these frames are used for channel measurement.
Okay, got you.
Another question is why we cannot dynamically choose epsilon for epsilon greedy algorithm. If you change epsilon dynamically, like you decrease it with time, in the end, you need to still keep it at some constant rate, at some low constant value, to avoid that you maybe estimated the statistics incorrectly and still using non-optimal rate. But if you don't decrease epsilon to 0, then you will have linear regret because you'll still spend some time trying random rates. The reason Thompson sampling achieves sublinear regret is not only because it stops uses less time to sample random rates, but also because it doesn't choose data rates for exploration randomly. Even when we explore different rates that are not currently optimal, we still don't choose rates that are obviously non-optimal. Another question is about minstrel, why MCS that is used on the third step and on the first step are not the same. Like why is the MCS with the highest probability, successful transmission probability, and the MCS with lowest rate are not the same? The difference is that MCS with the highest transmission probability used on this step uses success probability that is estimated from the statistics. And it's not guaranteed that it will be the same as the MCS with the lowest rate. For example, if you have periodic interference, it's possible that if you transmit using the lowest rate, your frames will be long and they will collide with the interference. But if you increase the data rate and your frames will become shorter, it's possible that they will actually have higher transmission probability because they have less chance of colliding with the interference. Another question is in which metric Thompson sampling was proved to be optimal. When we talk about this paper that proves that Thompson sampling is optimal, optimal here means that it has optimal asymptotic regret. Optimal means that as the time goes to infinity, the regret as a sum of the regret over all the time of the experiment will be on the order of a logarithm of the time. But this optimality is only asymptotic. So what was proven there is a asymptotic optimality of the regret. And it was proven for all possible environments, that is, all possible sets of success probabilities.
Alexandra, thank you for your interesting talk. My question is about aggregation, which is used in modern Wi-Fi networks. Does this algorithms you're talking about take into account that packets are not sent one by one, and they are usually aggregated in a single transmission, and we usually select modulation coding scheme once for this transmission, and the number of packets in this aggregated transmission can be different. Is this taken into account in this algorithm?
Yes, because in this NSA simulation, all these algorithms use IMPDU aggregation. So each frame consists of multiple subframes. And when the modulation coding scheme is selected, all the subframes of the transmission use the same rate. But after that, when we receive block-arc response, we look at the reported success or or failure of transmission of each subframe and update the statistics accordingly for each frame.
But maybe we should take somehow into account that we have aggregated frames. Maybe it will help, or just we can do as you propose. And so, okay, can we gain?
There are some
something
approaches that sometimes look at the aggregated frames, and if there are multiple subframes that are lost in a row, then it can be treated as a collision. Currently, for particle filter, I assume that the collision probability is some constant. In this case, I use an inverse of the contention window. But if we actually look at the subframes of an aggregated frame, we can probably better predict when the result of when the failure of transmission is the result of a collision or the result of a low signal-to-noise ratio.
Okay, thank you.
This is one of the approaches that is used by modern algorithm like Minstrel, but I don't think they provide too much gain compared to just collecting the statistics. Are there any other questions?
Okay, maybe I have a question about different packet sizes, because in general, the probability of success depends on the packet size. So you need to test your probabilities for different modulation encoding schemes and also for different packet size, how to do that.
In this case, I don't control the packet size. Do you have a question about adding the control of the packet size to the rate control algorithm, or to separate the statistics that we collect for different packet sizes?
I mean that if you transmit packets of different size on the same modulation encoding scheme, they have different probability of success and failure, and you have the only single statistics for any packets of any packet size, if I not misunderstand something.
But this is a problem only for the original Thompson sampling approach. If we take model-based approach, then the only parameters that we estimate is the signal-to-noise ratio. And from this signal-to-noise ratio, we can calculate success probabilities for different packet sizes. And these success probabilities will be different.
Okay.
So this problem can be solved by using model-based approach. That's another advantage of the model-based approach, that you don't need to collect different statistics for different transmission power and different packet sizes.
But it significantly depends on the channel model.
The state of the channel.
How well you know the channel model now becomes important for this model-based approach.
So I guess that's all questions for today. Thank you, Alexandra, for your interesting talk and answers for a lot of questions. And thank all the listeners for participation and for questions. See you next week at the next seminar. Thank you.